All right, this is chapter 8 on mass movements. This first section is going to be on pretty much the causes and basics of mass movement. So, mass, wasting, landslides, they're both kind of like general, overall encompassing terms to just mean when uh, Earth moves downhill. Um, Movements can be slow and subtle, where you don't even notice them, or they can be sudden and swift, like a large avalanche. Oh yes, and then the figure there shows landslide potential. So if you look, it's in pretty much hilly areas. So you've got the Sierra Nevadas, the coastal mountains here, the Rockies, the Appalachians, the Wachita. I'm not sure how to say it. Mountains right around here. So where you have hills, you can have landslides. Okay, so what influences slope stability? So slope stability is if that slope or hill is stable. So it all comes down to the physics, of course. So the shearing stress is pretty much, if you remember, we talked about shearing stress is like tension was pulling apart, compression was squishing, and shearing was sliding past one another. And so here, as this is coming down the hill, it's sliding past this underlying material. So it's a shearing stress. This diagram showing, of course, gravity pulls straight down. Uh, Friction is going to reduce the shearing stress. And then we have this shearing stress of things wanting to slide down the hill. Um, so what can happen to decrease the slope stabilization? So if you have a slope that is stabilized, if you decrease friction, so if this becomes less, then your shearing stress is going to override and it's going to start slipping. What can reduce friction? The most common thing is adding water. You just think of a slip and slide versus like a dry slip and slide. Obviously, you're going to go down the wet slip and slide much easier. Um, or you can just reduce the sheer strength of the rock itself by like weathering it and just making it not as strong. And so shear strength is the ability of the material to resist shearing. So kind of how strong is the material, either the rock or the soil on top of it. Um, so here is the angle of repose. The angle of repose is the natural angle at which a material can stand without starting to slide. And so a lot goes into that. The characteristics of the grains or soil itself, some can be kind of stickier than others. They can stand higher. Um, the grain size comes into play and the grain shape. So this is showing angular grains have more friction. They can kind of jet together and piece together more like bricks than rounded grains. Rounded grains, if you just think of like a ball pit, you're not going to get to that ball pit to stand up very steep. But you could get a lot of, really, if you just think of your normal chunky rock, you can get that to stand up much steeper. Um, as well as some material is just naturally more cohesive, meaning it has like almost like static electricity properties that help hold it together. Water plays a large part. So a little bit of water helps it stick together. So if you think of like a sand castle, if you try to just make a sand castle out of like dry sand in like your um, sandbox in the backyard, it's not really going to stand up that well. But if you go to the beach where it's got some water in it, you're going to be able to make a sand castle and it's going to stand and have, perfectly vertical walls and things. But now if you add too much water to that sand castle, it's just going to become mud and you're not going to get mud to stand up at all. Um, and then kind of the physics behind it, you have in the pore space, which again is the void between grains. If you get a lot of water in there and you have too much water pressure, it's going to push apart those water grains. So if I try, let me see if I go back and do the drawing thing. Um, so if we have these grains together, like so, okay, obviously that's not perfect, so I'm trying to draw with my mouse. Um, you have these pores, that is not blue. You have these pores in here that can fill with water. And if it fills with too much water, you get too much water pressure, and now that water pressure is actually going to start pushing apart the grains to the point where they may not even be touching at all, which is the case with quicksand, or to where they're just not touching as much, and it just reduces the strength of the soil. Frost wedging is when this water freezes and it can make cracks and uh, break rocks actually if the water gets into a crack that's already in a rock or um, and then it freezes. Expands when it's water expands when it's frozen. I think we all know that. And so that makes the crack bigger and bigger, and it can actually break large pieces of rock off. And frost heaving is the expansion of wet soil as it freezes and ice expands. So, kind of like frost wedging, but not in big rocks, but in the soil. And then the soil can come up and it loses a lot of its strength in that here. Here's just a map. I think this was Puerto Rico showing the number of landslides that happened after a hurricane because all the slopes became saturated. And vegetation. So kind of like water, vegetation can play different roles. Small vegetation like grass and things like that are help stabilize the soil. Um, so the roots kind of, have you ever tried to like pull up like grass? It's like all connected in like a mat. And so that mat of roots helps stabilize the soil so things don't want to fall out and slide down as easily. Now, really, really big plants, though, like trees, those rocks can go in and tear apart bedrock. I'm sure you've seen sidewalks and roads and things that have been lifted up and torn up from tree roots. That can happen to the bedrock as well and destabilizes slope. Also, if the plant is too big and it's like at the top of the hill or it's not very stable, draw again. So you have something like this. Of course, I'm exaggerating. I don't know why it's giving me a straight line. And then you put this huge tree right here. That's a lot of weight that you've just added to what could potentially be an unstable slope. Plus, you get the tree roots that's going to start breaking things up. You can imagine you're going to start getting some rock falls, or if this isn't soil, you're going to start getting some slides or flows. Um, so this is okay. So it can be good. So plants can provide strong interlocking networks. Also because the plants, use the water, can help kind of dry out the soil so it won't become oversaturated. But yeah, they can stabilize too. Um, and then if you have slopes that have had a lot of vegetation on it, and that vegetation is removed by either by like wildfires or just human activity, then you're taking away something that was helping to stabilize the slope, and it's more likely than to have landslides. And you see that in California, like annually. Um, Earthquakes, we already talked about liquefaction and some of the effects of this. That is not push. There we go. Landslides are very common with earthquakes because you're shaking the ground. And if you have any kind of water in that soil or anything that was, just about to fall off, you're going to shake it off. It jars apart soil particles and rock masses, reduces the shear strength and friction. Again, if you remember what I drew about the grains being all kind of stacked together, you start shaking that, they're going to want to like spread out. Um, and you can't have an immediate movement. Turbidity currents are pretty much landslides that happen in the ocean. Um, all the sand and stuff like just comes coming down, usually through like a canyon or something. It almost looks like a pyroclastic flow, but with dirt in the water and it just flows along the ocean floor. And it happens along the coast, and earthquakes can cause these to happen, as well as anything that can destabilize a slope. It could be major hurricanes and things that could happen and cause the turbidity currents as well. Quick clays. So these are from rock flour, which are rocks that have been ground by glaciers in the past. They've just been pulverized into what we call flour. So just imagine flour. And then they're deposited, it gets washed downstream. They're deposited in that shallow marine environment, which is just like pretty much like the coast, but not the beach, in the ocean, near the shore. Then, as things are uplifted, they're brought out of the ocean, but they have all of the salt water from the ocean in them. The water evaporates, and then all that salt precipitates, and the precipitation of the salt cements the grains together. But it's just a salt cementation. So as soon as you get some fresh water in there, the fresh water washes away the salt, and then you have this really loose rock flour. And so you can imagine that it's lost, and then once that cementation has been lost, then it's no longer stable. Um, and then, of course, if you get an earthquake, they can just, oh, the earthquake can break apart the glue too, or you can just get liquefaction if it's already kind of been broken apart. Here it says break apart the glue. It's talking about the salt cementation in there. Sensitive clays are pretty much like quick clays, but not from the glacial rock flour, from volcanic ash, but same concept. Although they are kind of even weaker, not just can they be broken apart by like earthquakes, even just the vibrations of passing automobiles can cause a destabilization event. Mm. Next, we will be moving on to types of mass motion.